Hi students, welcome to lesson 13.5, the law of sines. So we've spent the beginning of this chapter talking about trigonometric ratios in right triangles, and we even moved beyond acute angles into the coordinate plane, and we've looked at the unit circle, and we've explored how angles can have reference angles in other quadrants of the unit circle, and we've also talked about radian measures, so how that's a different measure of rotations. But what about acute triangles or obtuse triangles? I mean, we really haven't discussed, at least not in this course, what happens if we don't have a right triangle? So what happens if we don't have a hypotenuse, or we don't have an adjacent leg or an opposite leg? Because acute triangles don't have hypotenuse, and they don't really, unless they're isosceles triangles, have sides that are called legs necessarily. And the same with obtuse triangles. So what do we do if we have non-right triangles? Well, don't worry, because the ancient mathematicians thought about that too. And that's where the law of sines and cosines came from. Our focus in today's lesson is going to be on the law of sines, and in the following lesson, the law of cosines. And these are our two options when we are trying to maybe look for angles or sides in triangles that are not right triangles, so that the trig ratios are off limits. So this would be our backup plan, the law of sines and the law of cosines. Well, you may remember hearing about the law of sines and using the law of sines back in Geometry B, but I'm just going to do a little review as if you didn't really know the law of sines. So it turns out that no matter what kind of triangle that you have, it could be an acute triangle, a right triangle as well, or an obtuse triangle, the ratio of the sine of an angle to the side across from it is always equal in that triangle. So if you say, for instance, in this drawing here, you looked at the sine of this angle A, and you compared it to the side across from it, and you took the sine of angle C, and you compared it in a ratio to the side across from it, and then you did the same thing for angle B and the side across from it. It turns out that in a specific triangle, those ratios will always be equal. And it really kind of comes down to what we learned about in Geometry A, about the relationship between the angle and the side across from it. You know, the bigger you think about an angle, opening up the hinge of an angle, the bigger you make it, the larger the side across from it, and so on. So that means smaller angles will have smaller sides across from them, and vice versa. And that's why in a given triangle, because there is this relationship with the angles that they all have to add up to 180, that these ratios are always equal. And that gives us an avenue to try to work with finding parts in non-right triangles. Now you hear lots of different responses to this question. What do you need to use the law of sines? Well, I like to keep it really simple. I mean, some people will think about, they'll say, some of those, conditions of a triangle that you have to meet, like you have to know, two angles in the included side, like angle, side angle, those kind of things. But I like to keep it simple. Here's what you need to know to be able to use the law of sines. You need to know both measures of one angle side pair. So if you have that, if you know, say for instance, the measure of angle B and side B, which would be across from it, then you'll know both values in one of the ratios. And really the way the law of sines is we don't use all three ratios at once. We just pick two at a time. Like for instance, you could use the sine of A over A and the sine of B over B and set those equal to each other. And when you have a proportion, then you can use the cross products. Or maybe we would be using instead the sine of B over B and the sine of C over C. Or we could even use the pair, the outside pair, the sine of A over A paired with the sine of C over C. So it comes down to it. A quick check way to see if you can use the law of sines is, first of all, you want to see if it's a right triangle. If it is, your best bet is probably to go with one of the trig ratios. Although I did say you could use the law of sines and the law of cosines when we learned that for really any kind of triangle. But if it is a right triangle, I would go with SOHCAHTOA. Use one of your trig ratios. But if you have a side and an angle pair that you know both measures of, you can use the law of sines. So most of the time when we use the law of sines in Geometry B, we usually used it to find just like one measure. Like we would identify a side or an angle or whatever that we wanted you to find. Now we usually want to use the law of sines to solve a triangle. And what we mean by solving a triangle is this. It means to find all missing sides and angles so that by the time you're done, you know all three side lengths and all three angle measures. And so we're going to go ahead and start using the law of sines with this example. And when we do this, we're going to round all sides to the nearest tenth, and we're going to round all angles to the nearest degree. So we're given this handy dandy little table here where we can record all of these measurements so that we know when we're done, but some of them we actually already know. We already know the measure of angle M. It's 106 degrees, so we can write that one in. We know the measure of angle P, and that one's 56 degrees. And if we actually know two angles in a triangle, we absolutely know the third angle as well, because the three angles have to add up to 180. So I can very easily go up here and find the measure of angle N. It is 18 degrees, because that is the rest of 180. So they won't always be that easy to find the angle measures, but in this case, we were given enough information to just find it using the triangle sum theorem. Now I also know one of the sides. I actually know this side right here that is labeled as 1.5, and that has to be side N because it is across from angle N. So I can go right over here and list that one down. I have side N is 1.5, and that means I am left to find side M and side P. Okay, so when I use the law of sines, I like to start off by taking a look at my triangle and matching up the angle side pairs. And I like to do them with like little loops. So I take, you know, my highlighters or whatever, and I'll circle the ones that go together. So I know that angle N and side N go together. So I've got that angle N side pair. That's the checklist I have to make in my mind and say, can I use law of sines? Well, I've got that. Okay, so then I've got this pair, angle M and side M. And then I have a third pair, which is, let's see if I can grab another color, angle P with side P. And some triangles, because especially like this one where it's obtuse and really kind of a very large angle stretched apart, it's you know, sometimes not really clear unless you kind of draw a little arrow or circles or whatever to see which angle goes with which side. So this makes it very clear. So I know if I wanted to find the measure of these sides, I have to pick one of those proportions to write using those sine law of sines ratios. So the first thing I do is I always start off with the pair that I know both of. So I could say the sine of 18 degrees over 1.5 must equal the sine of, let's say I wanted to find side P first, so I'd say the sine of 56 degrees over P. Now I could have started finding M first, but I chose to find P first. And again, just one thing I said before, this is how we know we could use law of sines, is that we had that angle side pair. Well, remember, I didn't have that angle that was 18 degrees right from the start, so it might not be an angle side pair that you are given right up front, but if you can find it very easily, then you can also use the law of sines, as we did in this case. Okay, so now we have a proportion. So when we have a proportion, we can solve a proportion by just using the cross products. So if I were to multiply across, I would get P times the sine of 100, oops, not 180, but 18 degrees, excuse me, teaching geometry too much. I'm always thinking of 180, equals 1.5 times the sine of 56 degrees. Now, as a rule, I usually like to wait till the very last minute to have to grab my calculator. So I'm not at that point yet, because the next step, since I want to get P all by itself, I have to get rid of the sine of 18. And so I'm going to go ahead and divide both sides by the sine of 18 degrees. And Now that will cancel off these things and leave me with just p. So now I'm going to have to go to my calculator because I need to know what 1.5 times the sine of 56 degrees all divided by the sine of 18 degrees. So just to kind of be safe, it's probably a good idea to put parentheses when you go to your calculator around this part. So if you put this in your calculator, 1.5 times the sine of 56 in parentheses, then the divided by, and then the sine of 18 degrees, and this is what you should get. 4.024, which actually goes on, forever, but it's approximately 4.0 because they ask us to round to the nearest tenth. So I know that side P is about 4.0. And I want to put the 0.0 there because that reminds me that that's not actually exactly 4. It's not an integer value, but that was rounded to the nearest tenth. So that's 4.0. Now, if this were a right triangle, we'd have two sides, and we could use Pythagorean's theorem to find that missing side m. But this isn't a right triangle, and we know that acute and obtuse triangles don't have that relationship in the side lengths. So now what we can do is we can just go back and use the law of sines again in the same way that we did with this one. And you can start off now because you have two angle side pairs with either one, but I usually like to start off with the one that was given. So I'm going to start off with this sine of 18 degrees over 1.5 again. And then I'm going to set it equal to the sine of the other angle and side pair, which is the sine of 106 degrees, and it's across from the side that's m. So now I can do the exact same thing as far as solving goes. Just go ahead and perform the cross products, and I'll be multiplying m by the sine of I keep wanting to say 180 degrees, sine of 18 degrees, and that's going to equal 1.5 times the sine of 106 degrees. So same thing here, I'm going to divide both sides by that sine of 18, and then I'm going to go to my calculator. And the other reason I like to wait till the end to go to my calculator is you just get more accurate answers then, the less times you have to round. So I'm going to go ahead and put that in my calculator, and if you want to pause the video you can do that too, but you'll get a chance to try one here in a minute. And I got approximately 4.7 because it was 4.666062288, and that's all I could see on my calculator, but rounding to the nearest tenth then would give me this value of 4.7. And that would make sense that this was the biggest side in this triangle because of course it's across from the largest angle. And so now we can fill in the rest of our table. We know that side m is 4.7. We know that side P was 4.0 and side N was given to us as 1.5. And so that does it for that example. Let's go ahead and turn the page. Okay, so we're going to leave B for you to do as a you try question. So I'm going to have you pause the video and try this one. And just remember that when you're writing the ratios, you're matching up these angle side pairs. So your side E would go with angle E right here. Your angle D and side D would go together. And finally, angle F and side F would go together. And so, you're going to go ahead and fill in the parts that you know in this table here. And just keep in mind you can figure out this missing angle just using the triangle sum theorem. So really all you're left to find are side E and D. And feel free to look back at the prior example if you get stuck. But I want you to pause the video now and give this one a try. So I'm glad you tried that example, and I hope you were successful in finding the two missing lengths, side D, which should have been 17.4, and side E, which was 27.9. And if the triangle is given in units like feet or inches or whatever, be sure to give your side lengths in inches, but these didn't have units listed. But if for some reason you didn't get either one of those or one of those correct, be sure to make a note and bring that up when we see each other in class. We're going to move on to example C. And what I noticed about the next two examples is that they were just sort of more of the same. And we've done a lot of practice with this in Geometry B, and now we've done a couple together here today in class. So I want to make sure we cover the other case, like if we're trying to use the law of sines to maybe find angle measures. Right now, so far, we've only used the triangle sum theorem to find the missing angles because we were always given 2, and that allowed us to find the third with the triangle sum theorem. So we're going to make some changes to the next two triangles, and that way we get to see the other possibilities. So in this triangle, there was already some angle measures listed and a side length listed. So we're going to go ahead and I'm going to erase those. I know you can't erase them on your paper, but you could cross them out. So we're going to get rid of the 2 angle measures and that side length that's given. So get rid of this and the side length. And we're going to change these to the angle P being 101 because that is an obtuse triangle. So we're going to make an obtuse angle. The side across from it, we're going to make it into 20. And then we'll make this side right here, side R, we'll make it 14. So what we're trying to find now is angle R, angle Q, and side Q. So let's go ahead and list our things that we know in our table. So we know angle P, it's 101. We've got to find angle Q, and we've got to find angle R. And we know side P. So we know side P because it was given to us. And we also know side R because it was also given to us as 14. Okay, so I have the prerequisite for using the law of sines. I have this angle side pair that I know both values for. And say I want to start off finding the measure of let's go with angle Q first. I'm sorry, we have to find angle R first. And the reason why I have to do that is this. I know one of this pair. So I have to know all of one pair, and I have to know one of another pair. So that when I write this ratio, this proportion that compares these two ratios, I know 3 of the 4 things. So I could start off by saying the sine of 101 degrees over 20 is equal to the sine of, well, this is what I don't know. I don't know the angle R, so the sine of R over 14. So we've done some work with finding, angles before in the prior lessons, and we used inverses for angles, right? So we know that at some point we're going to have to use an inverse trig ratio to find this angle measure. So we're going to go ahead and do the cross products first. So when we do that, we end up with 14 times the sine of 101, and that equals 20 times the sine of R. Well, my next step would be try to get the variable by itself. Well, it's got a 20 being multiplied by it, and then it's got the sine operation that's with it as well. So what I have to do first is get rid of the 20. So I've got to do that. On both sides, I'm going to divide by 20. Okay, and then that leaves me with all that's left here on this side is, I'll just kind of erase this part, when I divided both sides by that, is I've got the sine of R. Well, remember, you can't just divide both sides by the sine. It's not that kind of operation. But we think about when we divide, it's because we're undoing multiplying and they're inverse operations. Well, the inverse sine is actually the inverse operation to the sine. So we use inverses for angles. That means we're going to have to take the inverse sine of both sides. Now, it's possible to do this all in one step, if you want to. If you feel uncomfortable with that, go ahead and figure out what 14 times the sine of 101 is divided by 20, and then take a decimal equivalent to that and take the inverse sine. But you can simply put this in your calculator all in one step, and this is what it would look like. You'll have to make sure that after you hit the inverse sine, you make a parenthesis and include all of those things, the 14 times the sine of 101, and then close the parenthesis on the degree measure divided by 20 and close the parenthesis. That way it knows you want to take the inverse sine of this entire thing. But as long as you do that, you can do this all in one step. And it turns out that we can see here that that means the measure of angle R is approximately 43 43 degrees. They wanted us to round to the nearest degree, and so we're going to go with 43 degrees, and that's the measure of angle R. So we could fill that one in. Well, now that we know two angles, we can find the third angle just by taking those two measures away from 180, and that should leave us with 36 degrees for angle Q, and so we also know angle Q. So we know angle R is 43, and remember that's rounded, and then Q is 36 degrees. Okay, now if we wanted to find the missing side length, we could go back and use the law of sines in a similar way that we did in the prior examples, because now we have this other angle side pair that we know one of. So we could start off and we could say, well, we could really pick any of them, but I'm going to go ahead with the ones that were given initially. The sine of the 101 degree over 20, and then that's equal to the sine of 36 degrees, which is the one I just found, over Q. And now I can use the cross products to multiply across. This is what it would look like. Q times the sine of 101 equals 20. Oops, I'm running out of space here. Equals 20 times the sine of 36. And then my last step would be then just to go ahead and divide both sides by the sine of 101 and then go to my calculator. And it turns out to be about 11.9757, and so rounding that to the nearest tenth would be about 12. And so we could list side Q in our table now as about 12.0. And just to make sure we know it wasn't exactly 12, we put the 0.0 to know we rounded it to the nearest tenth. And so through this example, I hope you can see that really you can use the law of sines whether you've got to find sides or angles. It really just involves you having the prerequisite information, which means you have to have an angle side pair where you know both of the measures. And so we're going to end the lesson here, and we'll just skip this last example because this is another one of the ones where you just have to find the side length. So I think we've practiced a couple of those, and we're just going to skip this one, cross it out, and we'll be done for today. So I'll see you in class.